Last class we talked about a discrete random variable x, and we talked about the ways to find the mean and standard deviation for that variable. Today we're going to go a little bit further into this idea of a discrete random variable, into a very particular type of discrete random variable called a binomial probability distribution. A binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are only two outcomes, two mutually exclusive outcomes. We will call them the success and the failure. Not necessarily that the success is a good thing, but we'll say that's what we're looking for, the success. Failure is what we're not looking for. There are only two options. Experiments in which only two outcomes are possible are called binomial experiments, provided that they meet four criteria. Criteria number 1, there has to be a fixed number of trials. So you tell me you're shooting a basketball 8 times. It's a fixed number of trials. The trials are independent. One shot of the basketball does not affect the second shot of the basketball. They are independent of each other. There are two mutually exclusive outcomes. I either make the bucket or I miss it. Two options. And the probability of success is the same for each trial. For me shooting a basketball, it's real bad. But it's the same each time. If we have those 4 things, a fixed number of trials, independence, two mutually exclusive outcomes, and the probability of success being the same for each trial, you have a binomial distribution or a binomial experiment. 2 options. Binomial means 2 terms, so 2 options. For example, U.S. women's soccer team is doing some calculations to help prepare for the upcoming World Cup. They are convinced that the toughest matches are likely to end in a tie. These matches require a shootout to break the tie, where each team gets 5 penalty kicks. They believe that they will need to make 4 or more penalty kicks to win the game. Over the history of the World Cup, about 70% of penalty kicks in a shootout are made. Let's assume that this is that the probability for each of the players on the U.S. team is 70% and that each kick is independent, so that we have a binomial experiment. First question is, what is the probability that the team will make all 5 penalty kicks? So let's back up. What's the probability that they make 1 penalty kick? And how many times is that happening if we make 5 penalty kicks? 70 times 70 times. We're doing it 5 times, which means we are calculating based on what we learned in chapter 5, that 70% raised to the 5th power, because we're doing this experiment 5 times. So 0.70 to the 5th power. I assume you want to use your calculator for this and not Excel, but mathematician's choice. Can you please find 0.70 raised to the 5th power? However you would like to find it. 1681.1681. We're going to round to 4 decimals today, by the way, for pretty much everything we do, unless it rounds cleanly before that. So that's the probability that we make, we being the U.S. Women's World Cup team, we make the 5 penalty kicks. 70%, 5 kicks. What is the probability that we make exactly 4 of the penalty kicks? So let's say the first 4 we make and we miss the 5th one. So that means we're taking this 0.70 and having this occur 4 times. But then we miss one. If 0.70 is the probability of us making a kick, what's the probability of us missing? 30%. So that means we have one of the kicks, that's 0.30. Can you guys calculate that for me? So 0.70 raised to the 4th power times 0.3 raised to the 1st power, because that's 4 makes and 1 miss. Four decimals, please. Oh, sorry, was that your question? No, what was your question?
Can we put it in the same equation, or are they different?
Oh, they can be all in one line. Sorry, I misunderstood your question. What did you guys get for this probability? 0.0720, correct? Okay, now is this the only way that I could make 4 and miss 1? Because I made the first 4 and I missed the last one. What's another way that this making 4 and missing 1 could happen? This one I'm missing the 5th kick. What else? I could miss the first kick, right? So another way to make exactly 4 penalty kicks would be to miss the first one and then make the next 4. Are y'all cool with this notation for making it and missing it? Okay, cool. So if I'm calculating this probability where the first kick I miss it, that's the 0.30, and then 4 in a row where I make it, you might be able to predict the future here, but if you type that in a calculator, it's going to be the same, because I'm still multiplying 0.70 times 4 times itself, so 0.70 times 0.70 times 0.70 times 0.30. I'm just doing it in a different order. Multiplication can happen in any order, so you're correct. We would end up getting the same probability. Interesting. What do we notice? Oh, look, we already noticed it. They are the same. So we're saying here that so long as we just miss one of them, because they're independent, it doesn't matter if I miss the first one or the last one. Any of those times is an option for me to make 4 and miss 1. How many different ways are there, though, of making exactly 4 and missing 1 of these penalty kicks? Here's what you've already told me. We had the one where we made it, and missed. And then we had the one where we missed it and then made it 4 times in a row. What's another option here? Make, miss, and then make the rest. What else? So you missed the middle one. Is there any other one? That's it. So how many different ways can this occur? 5 different ways. So there are 5 different ways for us to take 5 things and choose 4 of them to be our make the goals. So overall, what is the probability that the team will score on exactly 4 of the penalty kicks? Because here's what we did. We found this probability, the first option, to be 0.0720. We found this probability to be 0.0720. What would this probability be? And then this one. And then this one. So what should we do with these things to find the total probability of all of these options? We have this probability, this probability. They're all the same. So what do we do to find the total probability? Add them up. This is independent events that we're adding up. So we're doing 0.0720 plus 0.720, but we'd have to do that how many times? 5 times. So instead of doing it like that, because that's super inefficient, we can just do 5 times 0.0720, which would give me an overall probability of 0.36. And then if we had kept more decimals, which we're going to want this for a later problem, it would be 0.2. I know if you were to do that in your calculator, it would be perfectly 0.36. But just trust me, we want that last 0.2. Now, this was a really, yes, sure. Why did I not raise it to the power? So I'm finding this is already raised to a power. This was 0.70 to the 4th times 0.3 to the 1. There's just 5 different ways where this could happen. Because I could miss the 1st, the 2nd, the 3rd, the 4th, or the 5th, but only one of those. It's 5 different options. So I have to add together these independent probabilities to get the total. Now, one student calculated the probability of making exactly 4 of the penalty kicks using this formula below. And I want you to trust me on this. So before we do anything else, can you type this into your calculator? 5 times 0.07 to the 4th times 0.3 to the 1st. What did you get when you typed that in? It should be 3602, correct? 0.3602. That's exactly what we got when we went through this whole long process to find out this probability. So let's talk about what each of these numbers gives us and how we can more efficiently find these different probabilities. The number 5. I think you guys know what that one is. What was the number 5 from?
The 5 different ways.
The number of ways. So this is the number of ways to make 4 penalty kicks. What would this number be? The probability that we make it, and then why is it raised to the 4th power? Because we're making, at 70% chance of making it, we're having this happen 4 times. So this is what I'm going to be calling the probability of success. Are we cool with that? Probability of making it. Making 4 of them, if you will. And then what is this one? The probability of our miss, correct? Now this formula is called the binomial formula. If I actually don't know what classes you would have learned this in. I know in AP Pre-Cal we talked about it for like a hot second. When we were expanding binomials in an algebra course, and we had this crazy long problem where the numbers kept getting bigger in one exponent and smaller in another, and you had to choose from Pascal's triangle, the number in the very front. If anybody knows what I'm talking about, some people are looking at me like, please don't make me do that. I'm not going to. That's what this is. This is the binomial formula that we learned in those previous courses. This is why we learn it for a binomial distribution problem. Now we're going to break this down on the next page onto how we individually get these without having to go through all the steps. So stick with me. Because the whole question here for the World Cup question, if it does end in a shootout, what is the overall probability that the U.S. team would win? Well, we said through our research that we think the U.S. team would win if we make all 5 penalty shots, kicks, wrong sport. And we think we would win if we make all 4. So we can take the probability from question number 1 at the top of our page, the probability the team will make all 5 penalty kicks, which is 1681.1681. And we can add this probability we found using our binomial theorem, binomial formula, or entirely of step 2, which is 0.3602, knowing that the U.S. women's team has a 52.83% chance of winning if they make it to a penalty kick. Our goal of today's lesson, though, is to really understand this formula here and how we can find it most efficiently. There are plenty of ways we can find this. Pascal's triangle, a whole bunch of work, but I'm going to make it very efficient for you. Is that cool? Fabulous. Let's look at another example, though, so we can learn through example. On the back of this page, we're taking a pop quiz, and everybody panics. It's not real. But let's say you walk into a class, and there is a 5-question multiple choice pop quiz that you were absent for the last 3 weeks, and you literally have no idea what's going on. What are you going to probably do on that multiple choice test?
Yes.
Yes, cool. I want you to guess right now. I'm not going to show you the questions. I want you to bubble in 5 answer choices here. We didn't study. This is why you should study for stuff and keep up with the kid. I am right-handed. All right, let's see how you did on this random pop quiz. Here's the correct answers. Give yourself a check or an X if you got it right or wrong. The first answer was C. Second one was B. Third one was A. Fourth one was C. And the last one was D. Oh, I know. This is why we should study for stuff. I want you to count up the number you got correct and put it in that little blank. I got all 5 correct because I am the answer key, LOL. If we let X, our random variable, be not what you guessed as an A, B, C, or D, but the number of correct guesses that you got, let's check and see if this is a binomial setting. So we check our 4 criteria. The first criteria was that we had a particular number of trials. Did I fix the number of trials in this experiment? How many questions were there?
5.
There were 5 trials. So this is a yes. We had specific or fixed number of trials, and that N, the number of trials, was 5. You had 5 opportunities to get it right or wrong. Number 2, the second criteria is checking independence. Does you getting it right on number 1 affect your ability to get it right on number 2?
Yes, because technically,
Okay, no, don't make it weird.
it's not weird. Because what if you learn something on the last question that you didn't know, that you have to...
You didn't have the questions though. So in this experiment,
No,
did it change it? No, this has independence. Don't make it weird. This is an independent trial. One question doesn't change the probability of you getting the next question correct. The third criteria for a binomial setting is that we have only 2 outcomes. Based on the way that I am asking the question, whether that x is the number you got correct, are there only 2 mutually exclusive options? Not answer choices. Remember, the question is, the x variable is the number you got correct. You either got it right or got it wrong, correct? Which means that, yes, this only has 2 options. You either can get it right or you can get it wrong. Because specifically, that was what my random variable is, the number that you got correct. You either got it right or got it wrong. The fourth option, the fourth criteria, is that each has the same probability. What is the probability that you were getting it right each time? 1 out of 4, or 25%. All of them had a 1 out of 4 chance of you guessing it correct. So this is also a yes. We have the same probability for each individual trial. So since I said yes to all 4 criteria, this is a binomial, bless you, binomial setting. So what we're going to be able to do now, once we know it's binomial, is find out a lot of information about the distribution of each of the answer choices, meaning getting 0 correct, 1 correct, 2 correct, 3 correct, on and on until we get 5 correct. So we're going to use this formula. This is the formula for binomial that we actually did on the front page, but it looks horrendous when I write it in the letters it needs, which is why I wanted to show you it with numbers first so you're not scared of it. When we use this formula to find the probability of getting exactly 2 correct, what we would say is that the probability that x is exactly equal to 2 is the following. What was that first number on the World Cup example on the other page? 5. How did we get the 5? It was the number of ways we could pick 4 things out of 5 options. So 4 good penalty kicks out of 5 total penalty kicks. So what we're doing this time is we are choosing 2 out of the 5 questions to get correct. We need to know how many ways you can guess 2 out of 5 correct. So 2 choose 5 is how I say that. 2 choose 5. I will explain how to calculate that in a little bit. The next little dot, if we think about the World Cup example, was 0.70 to some power. That was our probability of success. What did you guys just tell me is the probability of guessing this correct? 0.25, correct? How many did we want to get right? 2. So the power becomes 2. Now, if we think about the World Cup example, the last number was 0.3. How did we get 0.30? Probability of getting it wrong. What is the probability of getting this wrong? 0.75. And how many will we get wrong if we only get 2 of them correct? 3. This formula is telling you to take the number you want, n, out of 5, the number of ways we can combine that, or choose that. The probability of success raised to the number of successes we want. The probability of failure, 1 minus that, raised to the number that's left. That's what this formula is telling you to do. You need a choose number, a success number, and a failure number. Now, how do we type this in? Great question. We're going to do this in one fell swoop. To get this, and let me highlight so we can find it a little easier. To get this on your calculator, you're going to type in 2 on your calculator, because that's the n. And then you're going to press math. You're going to scroll over to the probability menu, And I believe it's option 3 that says N choose R. Can somebody verify that that's the right number? Yes. And that's going to help us see how many ways we can choose 2 things out of 5. If you love Pascal's triangle, that is the second number in the 5th row. That's real embarrassing. Yeah, this should be backwards. N is the number of trials, which was 5. 2 is the number we want. So 5, choose 2. That's on me. I know. I'm going to chalk that up to a Monday. Sorry. Now, what does it tell you in the calculator? Great. There's 10 ways for us to choose 2 things out of 5 options. So in my calculator, to find this actual probability, I'm going to do 10 times 0.25 raised to the 2nd power times 0.75 raised to the 3rd power. And while I go answer the phone, can y'all answer that, please? So yes, when we calculate this, we should get 0.2637 as our probability. So a 26.37% chance of us guessing 2 of these questions correct. Now, doing this for every single option to create a probability distribution is pretty cumbersome because we'd have to do the combinatorics or Pascal's triangle and then do the trials and the failures and all that stuff. So instead, we're going to let Excel do a lot of the hard work for us. If we're wanting to make an entire table for all of the options for our binomial distribution, we would have to use this formula in Excel. Now let's explain this formula before you start using it. You're going to actually have to type binom dot, and usually after that it will start to try to suggest for you, bless you, the binomial distribution. So you can just press like enter and it will type it. The first number you type in is the number of successes, which is for us the number correct. So in the first cell that I'm doing this formula, I would put 0, comma, the number of trials, which is 5, comma, the probability of success, which is 0.25, comma, and then I'm going to put the word false. You actually have to type that word out. And the reason that you're saying the word false is because Excel is asking you, would you like me to do this cumulatively? Meaning, would you like me to do this number and every number underneath it? And your answer is no, because right now we are finding when x is exactly equal to a number. Exactly equal. So we are not doing cumulative probability, so we say false. Bless you. So for example, again, I'm going to write this down and then I'm going to switch to Excel so you can see it happen. I would make sure you've put this entire table in, this column in, because we want to label stuff, right? So I'd give it a title and then I would give another column for probabilities, but I would say equals binomial distribution 0, 5, 0.25, false. Because I want 0 out of those 5 trials to be correct when the probability of success is 0.25 and I don't want it to be cumulative. So I am going to give you some time to keep copying that formula down and practicing. I'm going to fill in my notes so you can see it whenever I put my iPad back up on the screen, but then we can just check our probabilities. A couple things I want to discuss about the formula just to make sure you understand. The reason that we keep using the word false is because we want exactly this many successes so that we can have a probability distribution of all of the options for us. So if I were to ask you, what is the probability of guessing exactly 4 correct? You would go, boop, boop, there's the probability. A 1.46% chance of that happening. Yes? Additionally, the reason the only thing that's changing in the formula is this number is because the only thing that's changing is the number we're trying to see you get correct. That has to do with this column right here. We are changing our random variable value in the formula, but the number of trials did not change, the probability of successes did not change, and we're not doing cumulative yet, so it does not change from false to true. Does that make sense to us? Fabulous. Yes, so if there were 10 questions on this quiz, we could go all the way to 10.
But you just have to change the other one.
We'd have to change the trials for that one as well, yes. Okay, now here's a little review moment. We're going to calculate and interpret the mean of the distribution using the formula from last class. So this is a great review, especially if you were not here last class, to realize that the formula for random variables changes how you find the mean and the standard deviation. So we have to look at our formula chart. We'll follow along together with this one. What's the formula telling me to do for mean? Look at that formula for mean in 5A. What is it telling me to do? Multiply what? Okay, because the formula is telling me to multiply the random variable times the probability of that random variable, Anna is correct. I have that in column A and column B. So I'm going to do equals A2 times B2. But since I want to do that for all of the columns, this is now where we can start to drag it down to all of the columns. After I multiply the random variable times its probability, what is the formula telling me to do? It's on the outside of that formula. The sum. So I'm going to come down here and I'm going to say that the mu, or the mean, I typed correctly today, would be equal to the sum. Now notice, it's starting to suggest things for you, correct? Use it. The mean, which is the sum of the product there, is 1.25. Now, let's say we don't want to build an entire binomial distribution for all of the options. Instead, upon starting this problem, we could have used the formula in 5B. What does the formula in 5B say all I need to do to find the mu? Look at 5B. What is it saying? Don't look at the board. I'm not showing you it on the board. What does your note say for 5B?
Use the formula for binomial.
Yeah, what is the formula? N times P. What is N? Number of trials. So for us that was 5 times P. What is P? Probability of success, which is 0.25. My friends, in Excel or in your calculator, please calculate what 5 times 0.25 is. What do you get? You get the exact same. Ooh, which means that we don't have to build an entire distribution table if we just have the probability of success and the number of options or number of trials. We cut down and we're able to work more efficiently. Likewise, what's your question? I did the sum of all of these probabilities. So the ones that you calculated in column C, I added them up. Similarly, we can do the same thing with the standard deviation formula. Let's review from last class. The formula is right there on your notes in 6A. What should I do first? Look at formula on 6A.
You have to multiply x times the mu.
I have to multiply them?
Subtract.
I have to subtract them. Okay, cool. So in the next column, I'm going to do the subtract step. That's not how you spell subtract. Please ignore. There we go. So I'm going to take the value of the random variable, 0, and I'm going to subtract the mu, what I just calculated, either in my calculator or in Excel. Now, if I want that number to stick in Excel, I have to put the little dollar signs around in front of C and in front of 8 so that the value does not change. Drag it down. After I subtract, what does the formula tell me to do? Square.
What did you subtract?
Look at the formula. What does it tell you to subtract? It says x minus mu. So I have a column titled x, so it's this minus the mu that we just found. And then I'm squaring that term. And I want to drag that down. Shift 6 and then the number 2. After I square, what does the formula on 6A tell me to do? Not yet. There's one more step. Multiply by the probability. That's the word multiple. Wow, can I not type anything correctly today? Okay. So I'm going to multiply the squared term times the probability. Good thing I have all my stuff labeled so I can find the probability. I want to do that for all. So no sticky on this one. Now, we've done everything on the inside of this formula for sigma. What should I do after I have the multiplying? I add it all up. So equals to the sum of, oh look, it's suggesting the correct cells for me. And then the very last thing is to do what? Square root. So I'm going to do equals the square root of that cell. This is what we learned last time. We have a little bit more explanation on these steps in the notes from last time, if you're needing more help. Now we get the sum. 0.9682 is what we get for our standard deviation. But if you notice, in letter B, we have a new formula for binomial variables to find the standard deviation. You have a question? If I've lost you on the steps from last class, good thing there's part 6B. Everybody look at their notes for 6B. There's a new formula we can use for standard deviation when we have a binomial experiment. That formula says to take the square root of n, which is the number of trials, times p, which is the probability of success, times 1 minus p, which is the probability of failure. So instead of having to go through literally all of these steps, if I know the number of trials and the probability of success, I can find sigma another way. And everybody's typing this one with me. I can do the square root of the number of trials, which was 5, times the probability of success, which is 0.25, times 1 minus that probability, which is basically the probability of failure, which is what? 0.75. Close parentheses, enter. Check that out. So even if I lost you in the sauce when it came to the 6.1, which go back to that because you have a quiz over that material next class. But for binomial data, we have a second formula we can use that will get me the same number, which means, again, I don't have to go through making an entire table. All I have to do is use the secondary formula, specifically if we know it's binomial. So the questions that we can start to ask and answer, I guess I should say, is questions like number 7 and 8. It says, what is the probability of getting less than 3 correct? Let's first off do this the easy way. You have a table. Which of the numbers in your table for x are less than 3? 2, 1, and 0, which means we could take this probability, and this probability, add them together. But that's very rudimentary. And what if we didn't have a table? Instead, we can do the following. To get something that is less than 3 correct, we're going to change the word false to true, because we can do a cumulative probability in Excel. If we want the probability that x is less than 3, first off, we have to change this to less than or equal to, meaning I'm going to change this to the probability that x is less than or equal to 2. Because aren't the numbers that are less than 3, 2, 1, and 0? So those are numbers that are less than or equal to 2. My formula only does less than or equal to. So you have to make sure you're writing it in terms of less than or equal to. Not less than, not greater than. Less than or equal to. In which case, I then can change my binomial distribution formula in Excel to be the number 2 out of 5 with the probability of success of 0.25, but this time I'm going to use the word true. Because when we use the word true, we're wanting a cumulative probability. Cumulative meaning add up everything underneath it. So this time in Excel, we're going to type this formula, and I'm going to show you this one, and I'll prove to you that. Doesn't matter where you do this. In fact, I'm going to just come down here. I'm going to do number 7. Doesn't matter. If I'm finding the probability that x is less than or equal to 2, I will do binomial distribution of 2 out of 5 with a 25% chance, but then the word true. I'm not going to press enter yet so you guys can catch up typing. When you guys do this, did you get, oh, I need more decimals showing. 0.8965? Awesome. Now, I want us to check our work to make sure we understand that this is working. So 0.8965 is what we think we should get when we add together the cells that contain the probability for 0 and the probability for 1 and the probability for 2. If I just add those together real quick to check my work and show more decimals because it's rounding, don't we get the same number? This is the exact same thing, but if you don't have a table fully shown, you don't want to have to build the table to answer this question. Bless you. You can use just this formula to answer it. Yeah. Now the last question on this page says, what is the probability of getting 3 or more correct? Let me come back to my iPad. 3 or more correct. So if we want the probability that x is greater than or equal to 3, because that's 3 or more, I need to somehow change this mathematical sentence to use less than or equal to's. But if I want something that's bigger than, and I can only calculate less than, we're going to use complementary probability of 1 minus something to go greater. And if we want things to be greater than or equal to 3, that means we don't want them to be less than or equal to 2. So we can do 1 minus that probability that x is less than or equal to 2 to find things that are greater than or equal to 3. Now we technically already found this number, my friends. This is 1 minus 0.8965. That's what we just got in number 7, which would give you 0.1035. But if you wanted to just find the probability of getting 3 or more correct and you had a table, just like in number 7, you could take the number for 3, the number for 4, and the number for 5 and add them together. Putting all this together in our vocabulary section, again, we've kind of talked about all of this. The criteria to call something a binomial, the 4 criteria, are a fixed number of trials, independence of the trials, 2 mutually exclusive outcomes, just 2, and the probability of the success has to be the same for each trial. If we can say yes to those 4 questions, trials, independence, 2, and the same probability, then we can use the formulas we learned today. Technically, the binomial probability formula based on algebra and Pascal's triangle is this bad boy, but you probably won't use it because instead, having to go through all of this mess, we're going to use the Excel version. Now, I want to make sure this is very clear. When we are talking about x being exactly some number, we use the word false. And if we're trying to find less than or equal to, and only less than or equal to, not less than, not greater than, less than or equal to, that's when we use the word true, because it's finding a cumulative probability. Now you can use that to your advantage, and the idea of complementary numbers, complementary probabilities, to find other probabilities, but it's just less than or equal to. We also had new formulas for mean and standard deviation if you wanted to add your little notations here as well. Remember, n was the number of trials. P is the probability of success. 1 minus p is the probability of failure. So without having to build an entire table to use our probability formulas from last class for mean and standard deviation, we can just use these. And then last but not least, we're coming back to that word unusual. I know you know this. What is the percentage to be calling something unusual? If it's 0.05 or if it's less than 5%, I'll just use 5%. We've always called something unusual if it is less than 5%. However, as a rule of thumb, because we're now looking at probability distributions that are distributed to semi-bell-shaped curve with a bell-shaped curve, we can go back to using that empirical rule from chapter 2. Chapter 2, that's the one with the you know what I'm talking about? And all the standard deviations away from the mean. We now can see that 95% of all observations lie within 2 standard deviations of the mean. That's what it says when you're 2 steps away on that bell curve on your formula chart, which means 5% of our data lies outside of it. So your unusual data, yes, is 5%, but also now means that we are outside of these 2 standard deviations away from the mean. We now have a second definition for unusual. That definition is mu plus or minus 2 times the standard deviation. 2 standard deviations below the mean and 2 standard deviations above the mean would be a part of that 5% of unusual data. So we can now tie this back into our bell-shaped curve from chapter 2. And before we get into some calculations, let's just make sure we understand how to determine if something is a binomial experiment. So for each of the following experiments, we're going to check the 4 criteria, and either if we say yes to all the criteria, say that it is binomial, and if we say no to one of the criteria, we're going to say no to binomial. So question 1A, it says a random sample of 50 college seniors is obtained, and the individuals selected are asked to state their ages. Okay, first question, is there a set number of trials? Okay, that's good. Are the trials independent? Yes, because the age of one participant does not affect the age of the second participant. Are there only 2 outcomes? No, there are not just 2 ages. So this one is not a binomial experiment. We had more than 1 outcome as an option, so it is no longer binomial. Bi means 2. A poll of 1,200 registered voters is conducted in which the respondents are asked whether they believe Congress should reform Social Security. They found 47% in favor of reform. Is there a set number of trials? Yes. Are the responses independent of each other? Yes. Are there only 2 outcomes? What are those 2 outcomes? Yes and no. In favor of reform, not in favor of reform. The 4th thing we have to check is that we have the same probability for each trial. Is that true? Yes. So this is a binomial experiment with an N of 1,200 and a probability of success of 0.47. With those 2 numbers, we could find the mean, we could find the standard deviation, and we could make predictions about the number of people who would be we would select exactly that many that want a particular thing. We just need N and P. Number C, 3 cards are selected from a standard deck without replacement, so the number of kings selected is recorded. Is there a set number of trials? Is each one independent? I heard no. Why not? Without replacement. Absolutely. If I pull a card the first time, it changes the odds of the second card being a king, specifically because it says without replacement. So this is not a binomial experiment. Letter D, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. Is there a set number of trials? Yeah, they're shooting 3 free throws. Yeah. Is one free throw independent of the other? Yes. Are there only 2 outcomes? What are those 2 outcomes? Makes it or misses it. Is there the same probability for each trial? Yes, which means that this is a binomial experiment. The n would be 3, and the probability of success would be 0.80. According to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of 10 is obtained and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. All right, check the 4 trials. Check the 4 criteria. Is there a set number of trials? Yes. Is each trial independent of each other? Yes. Are there only 2 outcomes? Are you sure? What's the question here again? Is chocolate your favorite or not? I'm not asking you what is your favorite flavor of chocolate. I'm asking, is chocolate your favorite flavor or not? Is that 2 outcomes? Yes. So how you ask the question changes whether you have a binomial experiment. Is there the same probability for each experiment, each trial? Yes. Which means that this is also a binomial experiment where the n is equal to 10 and the p is equal to 0.28. Again, how you ask the question is very particular. If I had asked their favorite ice cream flavor is recorded, no longer binomial. But is chocolate your favorite? That's a binomial. Does that make sense to everybody? Fabulous. Let's do some computations now. A binomial probability experiment is conducted with the given parameters. You're going to compute the probability of successes in the independent trials of the experiment. I'm going to set up the first one with you, but you're going to be in charge of setting up and finding the answers for the other ones. If I was told the number of trials is 10, the probability of success is 0.4, and I want to know the probability of selecting exactly 3, I would set up the following in my Excel. I would say I am finding the probability that x is equal to 3. I would do the binomial distribution of choosing 3 out of 10 with a probability of 0.4. And because I want it to be exactly equal, I'm going to put false. So here's how we're going to check. To make sure you understand how to use this formula, I'm going to tell you the answers to each one of these. You're going to have to make sure you know how I got that answer. I would recommend making sure you write down not only this first part with the P, the probability question, but also what you typed in Excel to make it happen, because your brain later will thank you when you can look back at these. Yes? Yes. So like I said, I'm going to pause it for a while, but here are the answers you should get for each of the questions. Let's see if you can make that happen. Awesome. Okay, so we feel good about B. For C, the trick was that if I want less than 5, that means I'm actually finding less than or equal to 4. So I'm doing the binomial distribution of 4 out of 11 with a 65% chance of success, and then the word true, that's the cumulative. And then we get to the last one. This one we're wanting x to be greater than or equal to 12. Well, if I want the probability that x is greater than or equal to 12, that means I don't want it to be 11 or less. Equal to 11 or less than 11. And if I don't want that, I want 1 minus that probability. 1 minus the probability that we get 11 or less. So if you have a greater than sign, you might want to highlight this, you're going to have a 1 minus. We have to use the complementary probability because our formula only goes less than. So if we want greater than, we have to do 1 minus. So in one cell, I can do this all at one time. I would literally type 1 minus, and then I would start my formula of 11 out of 20 with the probability of success of 0.75, and then the word true. Ooh, I got it all in there. So once you have a greater than sign, really slow down and think about not only complementary probability, but also what you don't want. If we want greater than or equal to 12, we don't want less than or equal to 11. So we do 1 minus what we don't want. Now for the last example here, example 3, we're just now going to put some context on these kinds of questions because those were just math questions, right? Now we're going to have to actually interpret some real questions. It says in a recent poll, the Gallup organization found that 45% of adult Americans believe that the overall state of moral values in the United States is poor. Suppose a survey of random sample of 25 adult Americans is conducted in which they are asked to disclose their feelings on the overall state of moral values in the United States. First things first, before we do any calculations, we check to make sure it's binomial. Is there a set number of trials? What was that? What is the set number of trials? 25. So our n is 25. Are they independent of each other? Yes. Do we only have 2 outcomes? Yes, because the question is, do you think the overall state of moral values in the United States is poor? Yes or no? That's 2 options. What's the probability of success? And that's the same for all of the trials. So we have a binomial experiment here, and now we can use all of the formulas we've done from class today. Part A says, find the probability that exactly 15 of those surveys feel the state of morals is poor. What kind of probability am I setting up here, a true or a false? A false. If I want the probability that I could pick exactly 15, and while I'm answering the phone, you guys fill out the rest of that. We should get for this one 0.0520. Is that what y'all got? Fabulous. Okay, so the next question again, we're just adding context. It says find the probability that no more than 10 of those surveyed feel the state of morals is poor. If we have the phrase no more than 10, what mathematical sentence can I write? Less than or equal to 10. So yeah, this one's easy. So we're looking for x is less than or equal to 10 because that's no more than 10. Which means I don't have to do anything crazy on this one. We're doing 10 out of the 25 with a 45% chance of someone agreeing that the state of overall moral values is poor. And this time we're doing true because we do want it to be cumulative. You guys calculate this for me real quick. We should, for that one, get 0.3843. We do that one? Okay. Find the probability that more than 16 of those surveyed feel the state of morals is poor. More than 16. Mathematically, that is the sentence x greater than 16. But I can't do greater with my formula, so how do I have to find this probability? I think I heard it. A 1 minus for sure, but what am I doing 1 minus of? 15, very good. Actually, psych, it is actually 16 this time. Why is it 16 this time? Because it says more than 16. So we can get we don't want it to be 16. We want it to be more than 16. So we do 1 minus the probability that x is less than or equal to 16. I fell for that trick the first time I did this problem. You can literally see it marked out on my paper. So thanks for falling for the same trick as me. Which means we're calculating in Excel 1 minus binomial distribution of 16 out of 25 with a 45% chance of success and the word true for cumulative. We should get, I know I might have gone faster than you had time to type, so sorry. We should have gotten 0.0174. Okay. Letter D, find the probability that 13 or 14 believe the state of morals is poor. 13 or 14. In the probability unit, what did I do with probabilities when I had the word or in between them? I added them. So what should we do with these probabilities? Add them. We're going to do the binomial distribution twice in one cell. You're going to do, my pen would work, probability that x is equal to 13 plus the probability that x is equal to 14, which means we are doing 2 binomial distributions. 13 out of 25 with a 45% chance of success. This one is false. And the binomial distribution of 14. False. You can do both of them at one time, or you could separate them into two cells. If you had a table, you would just grab the 13 and 14 probability out of the table and add them together. The last question we're going to answer two ways. It says, would it be unusual to find 20 or more adult Americans who believe the overall state of moral values is poor in the United States, and why? 20 or more. Mathematically, using the binomial formula we used today, if I wanted to find the probability that is 20 or more, how do I find that? 1 minus for sure, and 1 minus what number? Is this one 20, or are we going to go to 19 on this one? This one's going to be 19. Because if we want it to be greater than or equal to 20, that means it can be 20. So that means we don't want it to be 19 or less, because it can be 20. So we would do 1 minus that binomial distribution of 19 out of the 25 at 45%, and this one is true. I want to give you time to calculate this one, so go ahead and pull this one up in your computer. For this one, you should get a very small number. I got 0.0004. Is that what you got? Is that unusual? Why, specifically? Yeah, if I change this to a percent, that's still 0.4%, and that is less than 5%. But we also talked today about being able to answer this question using mean and standard deviation. So using our shortcut formulas, I don't want to call them that. That's actually, they're not shortcuts. They're efficiency formulas for mu and sigma. Can you please find me the mu for this data? Remember, that formula is just n times p. What was our n? 25. What was my probability of success? In Excel or in your calculator, whichever one is more efficient for you, can you do 25 times 0.45? I think I heard it from somebody. 11.25, right? That's the average. That's the mean. We also want to calculate the standard deviation using my efficient formula for binomial data, which is the square root of n times p times 1 minus p. Well, we know n, that was 25. We know p, that was 0.45. What is the 1 minus p thing again? If the probability of success is p, what is 1 minus p? Failure. So if it's a 45% chance of us getting it right, what's 55? So I'm going to multiply that by 0.55. In Excel or in a calculator, whichever one you're faster with, please calculate the standard deviation using the efficient formula. .4875. I'm going to keep all 4 decimals. Now, why were we doing this? It's because we have an ability to go back to our empirical rule now. What I'd like for you to do now that you have these two numbers, either in Excel or on your calculator, I need you to calculate mu minus 2 times sigma and mu plus 2 times sigma. So in your calculator, I need you to do this number minus 2 times this number, and then this number plus 2 times this number. In Excel or in your calculator. So 11.25 minus 2 times 2.4875 and 11.25 plus 2.4875. When you do the subtraction, what do you get? 6.275. I think my pencil just died. Let me charge it up for like 1 second and see if it'll come back to life. 6.275 And if you do the addition, now this is the boundaries for 2 standard deviations above and below the mean number of people who would say that they think the state of morals in the United States is poor. What number were we looking for again? 20. That's bigger than 16, isn't it? So it's outside of the 95% of our data. It would be considered unusual for that reason as well. So we would say yes again as well here, because 20 is larger than 2 times the standard deviation above the mean. So either way, yes because of the 5%, or yes because of standard deviations, both are appropriate ways to show that data is unusual in a particular binomial experiment.